We have an unusual looking equation involving the tau function, and the tau function is just a combinatorics function that actually counts the divisors of usually a positive integer input. And it's called tau these days in most textbooks, but I've seen it called little d. Vanden Eynden and Underwood Dudley used little d, I think, in the old days, that's what it was. I think pretty much it's predominantly just tau right now, and it counts the number of divisors. Now we have this equation. Let's just briefly do an example here to make sure everybody's clear on what the function does. Tau, that's how I'll make my tau. I'll make it fancy like that. Okay, we'll do tau of 10. Now it's easy to count the divisors of 10. It's 1, 2, 5, and 10 itself. Now 10 is not a proper divisor, but tau doesn't care about that. So this is equal to 4. Because the divisors of 10, it's a small enough number where you can list them. 2, 5, and 10. Like that, okay? So for small numbers, it's just easier to manually do it. But for larger and larger numbers, you need a way to do it that precludes the possibility of leaving some of the divisors out. And so, not surprisingly, the prime factorization comes into play here. And 200, I just picked 200 because you have two different non-1 exponents. 2 cubed times is 8, and then 25, right? Now, I'll just write down the answer right now and then explain why you have to increment. This is slightly confusing. The first time I looked at this, you have to add 1 to each of the increments. Notice you have 3 here where we do 3 plus 1. You have 2 here. We have 2 plus 1. That product is 12. So there are 12 divisors, positive divisors of 200. Now, why do we increment? Well, the simplest example I can think of, just looking at it here, would be 2 to the 0 times 5 squared gives you a divisor, right? Namely 25. 25 by mental math is certainly a divisor of 200 because 8 times 25 is 200, right? So the presence of this 0 means the exponents of 3 can range through 4 values, 0, 1, 2, 3, each time producing a divisor. And the same thing for 5. 5 can range through the values 0, 1, and 2. So that's why we increment. That's it. It's one of the simplest numerical or arithmetic functions. Okay. And notice we listed all the divisors of 200 without actually having to physically list them as we did in the case for n equals 10. Now let's move along and solve the problem here, taking advantage of this increment, the exponent result that gives you the number of divisors. And you do need the prime factorization for this to hold up. Okay. Now, so again, I think it's pretty clear that this definition, if you will, of divisors, how you count divisors, it motivates this as a potential solution. Now, where does the 3, the 7, and the 13 come from? Well, 273, and you certainly surmise this, is 3 times 7 times 13. And that's a necessary, the larger and larger your numbers, the more your comp time is done right here. In other words, here's where you're doing your comp time. For larger and larger numbers, it gets harder and harder to find the prime factorization. It gets to the point where you need computers, right? But for this, 3 times 7 times 13 is pretty easy to discover. And do note that 1 and 1 are the exponents, okay? Now, again, so far so good. So we're going to go down and we're going to substitute this sort of template, if you will, generic thing, into the equation. So here we go, y'all, just substituting it in. Tau 273 is equal, 3 times 7 times 13 is 273, and we've proposed this x to be our solution type, okay? And it has to equal to 3 times 7 times 13. Now, basic laws of exponents here, again, it's 3 to the first, 13 to the first instead of the first. That's why you have r plus 1, s plus 1, and t plus 1 now. And now the increment part is, we're going to implement that. So you would have r plus 2 times s plus 2. We're incrementing each of the exponents, adding 1. It's a computer term, I think. T plus 2. All right. Okay, and it has to equal to 3 times 7 times 13. And the prime factorization is so important here. To have the prime factorization really makes this thing more or less melt in your mouth. All right, so what do we need right here? We need r equals 1. We need it to physically equal 3, right? So 1 plus just the uniqueness of this, and that's how it has to be. So you have 1 right here, and this would force s to equal to 5. 5 plus 2 being the 7, you see. And finally, it would force t to equal to 11. Okay? And again, it's very easy there's no doubt that this is going to work if you substitute this back in. So the solution would be 3 to the first power times 7 to the fifth power times 13 to the 11th power. Okay, that's our solution. And I'm not going to take the time to write that in its Hindu Arabic form, right? Who wants to do that, right? But anyway, I think that does it. I'm making mistakes. 1 plus 2 is 3, 5 plus 2 is 7, and 11 plus 2 is 13. So this huge number, well, again, you could write it Hindu Arabic if you like it, but 13 to the 11th is already too big to say, right? So this is our solution, folks. And again, you can go ahead and try it if you want, but it's easy. The nice thing is you don't have to even know what the Hindu Arabic is. The law of exponents, it's going to work. If you take this and substitute it back in, it's going to work out nice and clean just by what we've been doing. Okay, that's all.